So good morning, everyone. I'm Rajdeep Singh, and today we will be discussing about theory of computation. So in this video, I'm going to introduce you with this subject and the related terminologies which we will be facing throughout this subject. So first of all, we need to know what are the prerequisite of this subject, what knowledge we should have in advance before studying this course. So one should have some basic knowledge of discrete mathematics. What are the strings, languages, and alphabets? What are the basics of data structures and algorithms? So if you have slight or basic knowledge of all these things, you can easily understand this subject. Now, what is theory of computation? So theory of computation is also known as automata theory. It is a theoretical branch of computer science which and mathematics which mainly deals with the logic of computation. Whatever computation we are performing with the help of computer, the logic of that computation is being dealt by this automata theory. The theory of computation is the branch that deals with how efficiently a problem can be solved on a model of computation. So we'll be discussing the model of computation here, which will be help to solve the problems which can be solved by the help of computers. Now, this theory of computation is actually divided into three areas. First one is automata theory. So at the very first, I will be discussing about automata theory. Then comes the computability theory. And lastly, we'll be discussing about complexity theory. So these are the three areas in which this theory of computation has been divided. Talking about the applications, the automata and this theory of computation is used in many areas. Like the first and foremost is the design of in designing the various phases of compiler design. We are also using its concept in text editor, as you can see in many text editor software like Microsoft Office Word, Notepad, and others. You can see the text editors there. These text editors are based on the concept of theory of computation. Spell checkers, vending machines, evaluation of arithmetic operations are the few basic application areas where the concept of theory of computations are applied. Few advanced application areas are like genetic programming, neural networks, robotics, and artificial intelligence. So it has a vast domain where its applications are found. Now I would like to discuss few terminologies which one should know, which one should understand before starting this course. So first of all, I would like to discuss what is the language. Any language, whether it is Hindi, English, or any computer language like Python, Java, etc. What a language should consist of. A language should consist of three things mainly. First one is a set of alphabets, means what are the alphabets that constitute the words and word of that language, any word of that language. So if I talk about English, it constitutes of 26 alphabets from A to Z. If I talk about Hindi, it consists of different sets of alphabet. If I talk about C++, it would be consisting of alphabets, numbers, and special characters. So different languages have different alphabet sets. So first thing is that a language should have set of alphabet. Now, second thing which we make out of that alphabet is word. So word could be formed by arranging those alphabets in a sequence, but that sequence should have some meaning. Like if we have three alphabets in English language, that is A, C, and T. Now, if I write it like this, ACT, then it does have some meaning. This act is a word which does have some meaning in the dictionary. If I write it like this, cat, it does also have some meaning in dictionary. But if I write tag, it doesn't have any meaning in the dictionary. So therefore, this is an invalid word for us. Similar is the case with other languages. If you arrange the alphabets in some order, it should have some meaning according to that language. According to the dictionary of that language, it should have some meaning. So set of valid words are required. And lastly, the most important thing is grammar rules. Grammar rules, or what we call as syntax in programming languages. Every language, I'm saying every language, whether it is English, Hindi, or any computer language, that must have some grammar rules. For example, in English, we write, first of all, we write subject, then comes the verb, and then comes the object. If we do not write a sentence like that, it will not have any meaning. Like if I write a sentence like this, this cat is, it does not have any meaning because it is not following the grammar rules of subject plus verb plus object. But if I write it like this is a cat, then you can see it does have a meaning because we are following some grammar rules. Similarly, if I talk about, let's say, C++, in C++, if you write int a comma b semicolon, then it will be valid. But if I write a comma b int semicolon, it will not have any meaning because it is not following the rules, syntax rules, which are there in C++ language. So any language should have three things, or any language constitutes of three things. First one is set of alphabet, second is set of valid words, and third is grammar rules. Now, this is all about language. Now I'll talk about what are the alphabets. Alphabets is nothing but those set of words or set of alphabets which you are using in language, and it is denoted by this symbol sigma. The symbol resembles the symbol which we also known by the name of summation, but here we will refer it with the name sigma. This sigma is used throughout the subject for the set of alphabets. Whenever we want to write set of alphabets, we will write sigma directly. Next thing is string. Now, what is string? So whenever you write down those alphabets, those whatever alphabets you have got in sigma, whenever you write a sequence of alphabet, you will get a string. Now it depends on from language to language that whether that string has some meaning or not. Okay. Now, next is a length of string. In the length of string, if I say, suppose use a string, use the name of string, and the string actually is cat. Okay. So if I say what is the length of string, then it will be denoted by this mod sign. Whenever we write mod u, that means I'm asking about length of the string. And length of the string is number of characters or number of alphabets used in this string. So here 3 alphabets are used, so the length of string is 3 here. And if suppose some string does not have any alphabet in it, then it will be referred with the name null string. And this symbol is also known as known by the name epsilon. Please remember this, because these terms will be there in throughout this subject. You will be facing these terms very frequently. So epsilon, what is epsilon? Epsilon is nothing but null string, a string which is having no alphabet in it. Okay. So what are the operation which we can perform on this string? So first one is concatenation. Concatenation of a string is nothing but when we join two strings back to back, then it is called as concatenation. Now, if, for example, if I took U as first string, that is cat, and V is another string, that is house. So if I have concatenated, the symbol for concatenation is dot. So I have written here u dot v. Whenever we concatenate those string, we will be getting cat house. Okay. Now this cat house has become single string, single entity. And one more thing which needs to be remembered, that concatenation does not follow the commutative property. That means if you have concatenated u with v, it will not be equal with when you concatenate v with u. Okay, because it will become house cat then, and then it will be two different strings in that case. Okay, so these are something some concepts about strings. Next is substring. Now, what is substring? So substring is very much analogous to what we have read in set theory. So subsets, just similar as subset, we see here substrings, but there is a slight difference in it. If you remember, a subset, suppose here a string is written here, that is cat, and we have to write its substring. So what we'll write? Epsilon, that means null string, just like we was writing phi in the case of set theory, null set. Similarly यहाँ पर मैं क्या लिखूंगा? Epsilon. Okay, then all these strings with length 1 will be written. So C individually, A individually, and T individually. Then string with length 2 will be written. So CA and AT will be written. So the thing which should be remembered here, and the thing which is different from the set theory here, is that I haven't written CT here. So CT cannot be considered as a substring because A will always come in between C and T. So you cannot separate C and T and write it alongside, because A is the alphabet which will always come in between C and T. So CT will not be considered in substring. And then we'll write a string with length 3, that is CAT. That means the string itself will come here. Okay. So these are the substrings, how we'll write substrings here. Now talking about proper substring. In proper substrings, only a CAT will be removed, just like proper subset, and all other strings will remain as it was in the set of substring. Similarly, non-null substrings, in non-null substring only epsilon will be removed and all other things will remain as it is. So this was about substrings. Now next is prefix and suffix. So if we consider the same string cat, what are the prefixes? Prefixes are all these strings which are coming in prefix of that string. That means epsilon will be there. That means before cat there is nothing. That means epsilon is there. So we'll write epsilon here. Then C, then CA, then CAT itself. Similarly, if you talk about suffix, so CAT will be there, then AT, then that means trailing part. T will be there, and lastly epsilon will also be there. So in both prefix and suffix, epsilon will be present there. In first one, prefix, the preceding set of strings will be written, and in suffix part, the trailing part of these strings will be written. So these these are all about substrings, and what are the null string, what are the languages, alphabets. So these are the related terms. Now I will move on to the very first topic of this subject, that is finite state machine. Now what is finite state machine? So finite state machine is a model, or you can say it is a logic which will help us to identify that whether you have whether it is used in two ways. If you have using a finite state machine as language acceptor, then it will work for the checking the validity of a string. But if you are using this finite state machine as a transducer, or if you say as a function computation. So it will compute a function and give a respective output on the output side. So we'll see that thing later. But first of all, how a finite state machine is defined. So finite state machine is can be defined with the help of 5 tuples. Now these 5 tuples needs to be remembered, that Q, sigma, del, Q naught, and F. So Q, capital Q, as you can see, is the symbol which we are using to represent the set of states. Whatever set of states our machine will be consisting. This sigma, as I've told you a few minutes back, that is, it is a set of input alphabet. Whatever input alphabet we are using in our language will be represented by sigma. Del is the transition function. Now, what is actually that function is, I'll discuss it after a few moments. For now, you just understand the transition function is a function which tells us the pattern of movement in a machine, or pattern of transition in a machine from one state to another. That means how by following what function, or by following what pattern, we'll be moving from one state to another. The next tuple is Q naught or Q0. It is the initial state, and it is one of the state from which is taken from Q. Okay, so that is why I have written here Q naught belongs to capital Q, and F is lastly the set of final states. So any machine can have more than one final state also, and this final state is used to check the validity of string. These final states will be from this set Q only. So that is why I have written F is subset of Q here, because some of these states of set Q will be designated as final states. And one more thing, in this finite state machine, F will never be equals to 5. Whenever we are talking about finite state machine as language acceptor, we will never consider this final set state as null set. Okay, so this is the formal definition of finite state machine, and this is in front of you is the classification of finite state machine. That means what are the different categories in which we construct our finite state machine. So finite state machine is classified into 2 categories or 2 classes. First one is finite state machine with output, and second one is finite state machine without output. By without output, we mean that it gives binary output in its output side. That means 0 or 1, or true or false, or valid or invalid. That means we are just checking the validity of a string. Now, if I talk about finite state machine with output, these machines are used to compute a function or to make some computation. Okay. Further classifying this finite state machine with output category, will be studying 2 machines that are Mealy machine and Moore machine. And the application of these Mealy machine and Moore machines are mainly in the area of digital circuit design. Talking about this another classification, that is finite state machine without output, that means it gives the binary output. We'll be studying 3 different machines. First one is DFA, second one is NFA, and third is NFA with epsilon. So DFA is its full form is a deterministic finite automata. NFA is non-deterministic finite automata, and third one is another variant of non-deterministic finite automata, that is with epsilon move. And the main application area of these machines are in the area of compiler design, in the various phases of compiler design. So these are the classification of finite state machine. Now, I will discuss few examples that how a finite state machine is designed or constructed. Suppose I've got an example of language set L, which consists of 3 strings, that is 0, 0, 1, and 0, 1, 1. So what I will be doing here, the first valid string in this language set is 0. So before starting this question, I would like to tell that how a language or how a string is said to be valid and how is it is said invalid by a machine. So after reading the complete string, if the control of the machine reaches to some final state, then the string is declared as valid. And if the control, after reading the whole string, if the control of the machine reaches to some non-final state, then it will be said as it is an invalid string. Okay. So let us start with this example. If the first valid string is 0, that means by reading 0, I will reach to some final state, isn't it? So what I have done, I have constructed here state A, which is initial state. An arrow will be made which is coming from nowhere, will signify the initial state here. Now what is to be done? By taking 0 as input, I have to reach some final state, because 0 is my valid string and first valid string of the set given L set. So I have taken 0 and reached to the final state B. Okay. Now what is to be done? Another string, another valid string is 0, 1. So what I will do, I will take the benefit of 0, which is existing in this machine, and I will make another transition of 1 and will reach to some another final state C. Okay. Now you can see that if 0 comes in the machine, it will reach to the final state and will say that yes, the string is valid. If a user supplies 0, 1 as input, then again it will read 0 and 1 and will reach to this final state C and will signify that this string is valid. Now talking about the third string, that is 0, 1, 1, what is to be done? Another transition of 1 will be taken and will reach to the final state D. Now you can see, if I get 0, 1, 1 as a string, I will read 0 from A and will reach to B, then 1 and then again 1 and will reach to the final state D, and I will declare that yes, 0, 1, 1 is also a valid string. Now if you see, if any other string other than these three string will come, this machine is not going to say that it is a valid. It will always signal that it is an invalid string, because this machine is only accepting three string, that is 0, 0, 1 and 0, 1. So in this way we will be making our machine or making a finite state machine by using our logic. Let us take another example. Now, before moving on to another example, I will also discuss what are the tuples by help of these machines, those tuples which we have studied in the introduction of finite state machine. So here, if I talk about set Q, A, B, C, D, all these things are states. So Q will be consisting of 4 elements, that is capital A, capital B, capital C, and capital D. Talking about sigma, sigma is the set of input alphabets. So all the alphabets which are written above these transition, these arrows are termed as input alphabets. So 0 and 1 are the input alphabet which we have used. So sigma is equals to 0, 1. Now talking about transition function, if you see here, I have written Q cross sigma maps to Q. That means whenever we have to make a transition, what are the two things which we see while making the transition? First one is that on which state we are presently, and what input alphabet we are getting. So the state is symbolized by Q, and this input alphabet is symbolized by sigma. So if you can see, this is the sigma and this is Q. By seeing these two things, we can decide that what is the output. So what is the output? Output is some another state. So what I have written in the output side, that I am mapping this to some another state Q. So in this way, I will write transition function of any finite state machine. Now this will be changing from machine to machine. I'll discuss it in later videos. Now talking about Q naught, the initial state here is A, so I've written A here, and final state B, C, and D, all three are the final state, so I will write here it in set F. So in this way I will understand what are the tuples of a machine. Now taking another example of finite state machine, that is 0 to the power n and 1 to the power m, where in this where n and m is greater than or equals to 0. So in this machine you can see epsilon is the part of this language, because if I put n and m as 0, it will become epsilon here. Okay. And n and m are since independent entities, so any number of zeros can come followed by any number of ones after that. So all possible strings of zeros followed by any number of ones, including epsilon, will be there in this language. Okay. So what we'll do, first of all, we'll make an initial state. Initial state will be there in every machine. Now, to accept any number of zeros, what I'll do, I will, first of all, since you can see that epsilon is a part of this language, so how can we reach from initial state to final state without taking any input? The only way is to make initial state as final state. So by making initial state as final state, we can accept epsilon in our machine. So epsilon is accepted here. Now, how we can make any number of zeros be accepted in this machine? So that can be done by making a self loop of 0 on state A. By this self loop, you can take any number of zeros in your machine, but it should reach to 1 after that. Okay, but there is no foundation for that there should be 1 after that only, because if I write m as 0, only 0 to the only zeros will be there in my string. So that is why this thing is valid, that any number of zeros will be on final state, so there is no problem. Now, by taking another 0, I will reach to some state B, and by taking a 1, I'll reach to some final state C. And for any number of ones, I will draw a self loop 1 over there and will take any number of ones there. Now, the question is why I have made this arrow of 1 from A to C. Because if suppose n becomes 0, then only any number of ones can be there in string. So what I have done, I will reach directly to C by taking 1, and then by taking any number of ones, I will be there in final state C only. So in this way, I can make the finite state machine of 0 to the power n, 1 to the power m. And another example where I have to make a finite state machine that accepts all the strings which is having odd number of ones. So for odd number of ones, what I'll do, by taking a single one, it should reach to final state. So I've done it. By taking 2 ones, where it should reach to some non-final state. So what I have done, I made another transition back to state A, which is non-final. So you can see by this small machine is accepting this whole language set, that if I take a single one, I will reach to final state. If I take 2 ones, so 1 and another one, I will reach to a non-final state. If I take 3 ones, so 1, 1 and 1, I will reach to some final state. So in this way, these machine can be designed by using your logic. For now, it is done. We'll be discussing about NFA, DFA, and other machines in next video. Thank you so much.